Hello everyone. Welcome to Neso Academy. We are learning theory of computation. And in the previous lecture, we have understood what are symbols, alphabets and strings. And in this lecture, that is languages and grammars, we are going to understand the remaining building blocks of theory of computation. So let's see all the topics of this lecture. Our first topic is languages, in which I will explain you what are languages in theory of computation. Our second and last topic is grammars, in which I will explain you how languages can be generated using the set of rules called as grammars. So let's begin with our very first topic, that is languages. So we have already covered the 3 steps of theory of computation, that are symbols, alphabets and strings. So we already know that symbol is the most fundamental or the smallest unit of ToC. Alphabet is the finite and non-empty set of these symbols. String is the finite sequence of these symbols from the alphabet. And now we are on the 4th step of this hierarchy, that is languages. So let's start our discussion on what are languages. So before understanding what are languages in theory of computation, let's first understand what are languages in general. So here I have taken an example of English language. As we all know, that English language is the collection of valid sentences. That means not every combination of words makes a sense. So if I have some words, combining them randomly will not create any sense. But if I combine those words as per the rules and regulations of English language, it will definitely make a sense. Let's understand this in a better way using an example. So here I have taken 2 sentences. The first one is, he is eating cake. Now this sentence is very much making a sense or meaning that the person is eating a cake. But when these set of words are combined randomly, like cake he eating is, now this sentence is not making any sense. This is the reason why this sentence is a valid sentence and this sentence is an invalid sentence. So this sentence will be the part of language, while this sentence will not be the part of our English language. So we can conclude that English language or even any language in the world follows certain rules to make the sentences. Only the sentences that will follow some rules and regulations as per the given language, those sentences will be the part of our language. So as we have understood that English language is the collection of valid sentences, similarly in theory of computation also, language is the set of valid strings. Here we have seen not every combination of words makes a sense. Similarly in ToC, not every string is the part of a given language. Only the strings that will satisfy some rules, some conditions, will be the part of the given language. So in the previous lecture, we have created multiple strings from the given alphabet. But all these strings will not be the part of our language. Only the strings which will satisfy the given condition will be the part of our language. So let's take an example to understand this. So here we have the condition strings with length equal to 2. That means only the strings having length 2 will be the part of language. So here I have taken 2 set of strings. The first set only contains the strings of length 2. You can clearly see all the strings are having length equal to 2. But in the second set of strings, this string has length 5, this string has length 4, and this string has length 1. That means none of the string in this set have length equal to 2. That means this set of strings is a valid set. And these strings will be the part of language, and these strings will not be the part of given language. So we can conclude that strings that follow the given conditions are the part of our language. So as we have understood the relationship between languages in general and languages in ToC, we are all set to understand the formal definition of languages in ToC. So here I have written, if sigma is the alphabet, then language L is a subset of sigma star. That is the set of all possible strings over an alphabet sigma following certain conditions. Don't worry, I will decode it for you. In the previous lecture, we have understood what is sigma star. It is the clean star closure, which is defined as the set of all possible strings over an alphabet sigma. That means it contains all possible strings of all the lengths over the given alphabet sigma. So it is a kind of universal set. And our language L is the subset of this universal set sigma star. That means language L will not contain all the strings contained in sigma star. Language L will only contain those strings from sigma star which follow certain conditions. That means we apply a given condition on sigma star and only the strings that will satisfy those conditions will be the part of our language. So I hope this definition is now clear to you. So let's take an example to understand this definition in a better way. So here I have taken the same binary alphabet, that is sigma is equal to 0, 1. And this sigma star is the clean star closure, which contains all possible strings of all the lengths over the given alphabet sigma. Now, as per the definition, language L is the subset of sigma star following certain conditions. That means we will apply condition on this set, and on the basis of that condition, we will find out that which strings should be included in our language set and which strings should be eliminated from our language set. So let's apply one condition. Strings that begin with 0. That means only the strings that begin with 0 will be the part of our language, and rest of the strings should be eliminated from this set. So let's find out. This is epsilon, our null string. This string does not begin with 0. That means we will eliminate this string. This is 0, which is obviously beginning with 0. That means this string will not be eliminated. This is 1, which is not beginning with 0. That means we will eliminate this string. Similarly, we will eliminate all the strings that are not beginning with 0. And we will get our language set as this set, which is only containing the strings that are beginning with 0. And these strings are the example of valid strings. And this language is an example of infinite language. Why? Because this set will further contain more strings that will begin with 0. That means this language contains infinite number of strings. And that is why this is an infinite language. Now we will take another example in which we will get a finite language after applying a condition. So let's take our example number 2. Here I have taken sigma is equals to lowercase a and lowercase b, which is the lowercase alphabet. And clean star closure will contain all possible strings of all the lengths over the given alphabet sigma. Now this time let's apply a different condition. So the condition is strings having length at most 2. Now here our language set will only contain the strings having length at most 2. Length at most 2 means that the length of the strings should be less than or equal to 2. Length cannot be greater than 2. So let's find out. Epsilon, that is our null string, has length 0, which is obviously less than 2. That means this is a valid string. A and B have length equal to 1, less than 2, and that is why these two are also part of our language. Similarly, these 4 strings have length equal to 2, again satisfying the condition and hence will be the part of our language. But the further strings like A, B, B will not be the part of our language because the length of the string is 3. And similarly, the string AAB, ABA, and so on will not be the part of our language because their length is greater than 2. So our language set will look like this, which contains the strings epsilon, A, B, AA, AB, BA, and BB. So these all are called as valid strings as per the given condition. So this set is an example of finite set, and this language is called as the finite language because it contains only 7 elements. That is a finite number. So I hope you all have understood what are languages in theory of computation. So in this way, we have completed our very first topic, that is languages. Now we will move towards our second topic, that is grammars. And as we all know, that be it English language or the language in theory of computation, it follows certain rules to make the sentences or to generate the valid strings. And in English, these rules are called as English grammar, which decide whether a sentence is valid or whether a sentence is invalid. So, to decide which sentence is valid, we use grammars. And these are some rules of English grammar. First, subject should come, then the verb, and then the object. Like in this valid sentence, first comes the subject, then the verb, and then the object. And since this sentence is as per the rules of grammar, it is a valid sentence. And this sentence is not according to the rules of English grammar. That is why this sentence is an invalid sentence. Similarly, verb must agree with the subject. Tenses should be maintained. So these are some rules of English grammar that are used to create the valid sentences in English. And similarly, in theory of computation also, we use grammar to generate the valid strings. Now you are all set to understand the formal definition of grammars in ToC. Here I have written that grammar is the set of rules required to generate valid strings of a language. It means that to generate the valid strings of a particular language, we require set of rules. And those set of rules are called as grammars. Let's see the next point. Grammar in ToC is represented by the uppercase letter G. Grammar is a 4-tuple, that is, G equals N, T, P, and S. Now, what is tuple? Tuple means the ordered collection of elements. And what is 4-tuple? It means that our grammar is the ordered collection of 4 elements. And these 4 elements are N, T, P, and S. Now let's see what are these 4 elements. N means the set of non-terminals or variables. T means the set of terminals or constants. P means the set of production rules, which are written in the form alpha tends to beta. And S means the start symbol, which is again an example of non-terminal. Now, to understand each one of them, let's take a simple example of grammar in theory of computation. So these are the rules of grammar. First rule is S tends to AA. Second rule is A tends to ABB. And our third rule is B tends to D. It simply means that S can be replaced by this term, A can be replaced by this term, and B can be replaced by this term while we generate the strings from these rules. Now let's understand what is N. N is the set of non-terminals or variables. And non-terminals are represented using the uppercase letters. So here, the set of uppercase S, uppercase A, uppercase B is called as N. and non-terminals are replaceable symbols. That means we can replace non-terminals by any other symbol while generating the strings from these rules. Now let's see what are terminals. Terminals are represented using the lowercase letters or numbers. So here in this grammar, the set of lowercase a, lowercase b, and lowercase d is the set of terminals. And terminals cannot be replaced by any other symbol while generating the strings. Now let's understand what is P. P is the set of production rules. So these all rules are called as production rules, and the set of all these rules is called as P. Now let's see what is S. S is the start symbol, which is also a non-terminal. That means S will be replaced by other symbols in order to generate strings. So the point from which we will start the string generation process is called as the start symbol. And in this grammar, S is the start symbol. Now, let's generate the string from this grammar. So first of all, we will apply the rule number 1, that is S is equals to AA. This is the start symbol, which is replaceable by this term. Now here you can see, this is a terminal and this is a non-terminal. Now I have just told you, terminal cannot be replaced by any other symbol, but non-terminal can be replaced by other symbols. And by applying rule number 2, we can see that A can be replaced by this term, A, B, B. So we will replace A by this term. And here we will get this term. This A is as it is, while this A is replaced by A, B, B by applying the second rule. Now again, these three are the terminals, while this B is a non-terminal. That means we can replace this B. So by applying rule number 3, we can replace this uppercase B by lowercase d. So we applied rule number 3 and we have replaced this uppercase B by this lowercase d. And in this way, we will get all the terminals in this string. And this is the finally generated string from these rules of grammar. And you can notice that all the symbols present in this string are only terminals. Now I hope that you have understood what are grammars. In this way, we have completed our last topic, that is grammars. Now we are done with all the building blocks of theory of computation, that are symbols, alphabets, strings, languages, and grammars. So this was all from my side for this lecture. Thank you, and I'll see you in the next lecture.